Hello, namaste, and a very, very good evening. You're back with me, Supriya Singhal, on this series for Modern Algebra, in which we are learning a very interesting and a very important topic called as modern algebra. So this is going to be helpful for BSc club people, MSc people, and also for people who are preparing for UPSC, CSC with mathematics as their optionals. So in this class, in the last class, we basically were covering some important questions. Some of them are previous year questions already. Some of them have been taken from very renowned books like on modern algebra. So you do not need to go and search for questions because I'm already giving you a lot of questions. So you can just suffice with these and just make sure that you are supplementing them with the previous year questions of your university or if you're giving UPSC, then UPSC. Okay, so in the last class I explained you that if there is something called as Z given, if there is something called as n belonging to Z given, and I told you that divide it into three parts called as Z plus, 0 and Z minus. And why did I tell you that? Because principle of mathematical induction can only be applied when you're dealing with the positive integers, not even with 0. So hence you need to basically segregate the cases and make it into three categories. So now your one question becomes actually three questions, so where you're proving the property for three types of sets. First is where your n belongs to positive integer, second where n is 0, and third is when your n is negative. And basically how do you start is you start with positive integers and prove them that by mathematical induction that property is satisfied. Then you do it for n equals to 0, and in the end you do it for negative integers, because what happens is for negative integers you're substituting your n by minus m, and you're just showing that if you replace n by minus m, then also left hand side will come out to be equal to right hand side. But in the end basically you have to write that using now principles of mathematical induction on m, you can show that. So hence always do positive, 0 and negative. Okay, that's the sequence you need to follow. So now in the last class I gave you this as a homework, but let's discuss because it's a pretty interesting question and an important one. And actually I think one of the questions, either this is a previous year question or something on this lines has already been asked in UPSC before. So just check your previous year question papers and you will find this question, or this sort of question at least. Okay, so now the question says that let G be a group of finite order, and you have to show that the number of elements X of G such that x cube is equals to e is odd. Show that the number of elements where x square is not equals to e is even. So now first of all, always whenever you read the question, mark the important words. So here just like see where my cursor is moving. The question first of all talks about G being a group. So basically your first given is that G is a group. Second given is that your G has a finite order. Okay, so your G has a finite order. This is your second property. Third property is basically it is saying that you basically now your to show is that you have to find n, which is basically number of elements, such that they follow this property. What is the property? That x cube is equals to e. Okay, and you have to prove that the number of these elements satisfying this particular property is odd. Odd means what? Is something in the form of 2n plus 1, where n can be any integer. So if you put n equals to 1 also, then you get answer as 3. If you put n equals to 2 also, you get answer as 5. So you always get is odd integers. So odd integers can be 2n plus 1 or 2n minus 1. Just a minute. Yeah, and the second part of the question says that you have to also show that the number of elements that will satisfy this property where x square is not equals to e is even. Okay, so now in this case, basically, as I told you in my first class, x is nothing but a dummy variable. You could have written a also, you could have written y also, you could have written z also, but just with the condition that x, y, z, e, whatever you are written here, basically comes from this G set. Okay, so now let's just prove the first part and then we'll show how to prove the second part. And I'm sure if I tell you the first part, you can easily solve on your own only second part. Okay, it's just about to tell you the method or the tricks of solving the question. So first of all, whenever I read the question, first of all, I see what is given. So I always write what is given. So given is that G is already a group and it's a finite order. So this finite order plays a very important role here. And I'll tell you why. So remember it's given that X is an element in the G. So now by closure I know that even x square will also be an element in G. X cube also will be an element in G. Why? Because X operated on X by closure property lies inside G only, right? So hence now x square lies inside G. Now x square on X also lies inside G. So in this way, if X lies in G, all its powers also lie in G. Okay, but there has to be a certain stop on the powers because it's given that the group is finite. Okay, and after that what will happen is that after certain power, basically the numbers will start repeating. Then only this case is possible, right? Otherwise this will become an infinite order. Oh, so first of all, what is order, right? Order just means number of elements inside the set. Okay, so here if G, suppose if I'm taking my group as a set of natural numbers or real numbers basically, then my order is infinite, right? Because there can be infinite numbers, but here it's given that the group is of finite order. That means there can be only finite number of elements inside this set. Okay, so hence I'm saying if I write x square, x cube, x4, x to the power 5, till I don't know what x ki power n lies inside this set, but I know there has to be one n at which this particular x to the power n will stop, because then x to the power n plus 1 and x to the power nth plus 1 term has to be one of these numbers which I've already written, because it is a group of finite order. Okay, you don't need to go into this much depth, and finite order you will actually be understanding it much more detail when I cover cyclic groups. Okay, so do not worry, just like this for extra information right now for this solving particular this question. Now just tell me, it is given that x cube is equals to e. Okay, now tell me one element where if I just do e cube, it will always give me e. Answer is e, right? Because identity, operated with identity, any number of times will always give me identity. So one element that will for sure follow this property is identity. Okay, so now remember my question was about proving that number of elements which follow this property are odd. So odd means I had to show that it has to be basically what? 2n plus 1. Okay, that means I had to find these many number of elements. So one element I've already found, which is identity. So now I need to show that there are 2n elements more. Okay, so how will you show it? See, x is already given. That x cube is satisfying e. Okay, so now out of this 2n also, one more I have basically solved. So if I basically can find a pair of x which also satisfy this property, and then I can say that, I found 3 elements, one identity, one x, and one the pair of x. So now look at it. So now basically I'm saying, suppose if G is a group, then if x is there, then even x inverse will also be there. Now tell me what will be x inverse ka whole cube. Okay, just solve it. So what will be x inverse ka whole cube? X inverse ka whole cube will be what? You write x inverse and then you basically do cube. And I told you that, basically algebra of powers is applicable in modern algebra as well. So you can take -1 outside and take 3 inside. So it will become x cube ki power inverse, and x cube is nothing but identity. And identity ka inverse is also identity. So basically you get that x cube, even x inverse cube is inverse, x inverse cube is also identity. That means if x cube is satisfying this property, then even x inverse cube is also satisfying this property. Hence, basically I'm saying, if I find an element A which belongs to this set, then even its inverse also will follow this property. Okay, and along with identity. So if I take x, then x inverse E. If I take y, then y inverse E. So now tell me, if I'm saying there are suppose n elements satisfying this property, then there will be, if there is suppose n, x, y, z, a, b, c, d types, there are n elements, like separate distinct elements which are following this property. Okay, and then I know that each of their inverses is also satisfying this property. So n becomes 2n and plus 1 for identity. So I'm able to prove that odd number of elements are satisfying this property. But the catch, and the biggest catch which will actually fetch you marks and can make you lose marks, like it's a very silly mistake, but something that is very crucial. And this is basically proving that x and x inverse are not the same elements. Because I told you, sometimes what happens is that your inverse of element is the same number or the same element. Then, all this basically calculation of yours will fail. Because what will happen is ultimately whether you write x inverse or x, since they are same elements, so it is not 2n, it's n. So here the catch is to prove that x inverse is not equals to x. Okay, so do not forget to prove it, otherwise you will not get any marks. And trust me on this, you will not get any marks even if you have written so much of theory and you have proved actually everything. Okay, so here this is all just what I just told you. For you have to find an x inverse which also satisfies the property, and now you have to show that x and x inverse are distinct or basically are unique. And I told you how to prove uniqueness, basically by proving contradiction. Okay, so you will assume that they are not they are basically same and they are not distinct. Okay, assume that x is equals to x inverse. Then what you do, you multiply x on both the sides. So here it will become x square, and here it will become x into x inverse, which will become e. And now you again multiply by x. So you get x cube as x into e, which is equals to x. But in the question what it is given, that x cube is equals to e. Hence, you are contradicting whatever is given in the question. Therefore, x and x inverse cannot be same and they are distinct elements. Okay. So this is like first of all proving that. And then I told you if I take x, y, z, a, b, c, something like n elements, then there has to be inverse also will satisfy, therefore 2n elements and 1 for identity, hence 2n plus 1. Okay. And now the second part you will solve on your own. I'll tell you the same trick. Now the second question was about showing that number of elements of x square which satisfy this property that x square is not equals to e is even. Okay, so how will you show it? So again, first of all, tell me if x square is not equals to e, then even x inverse ka square will not be equals to e, right? So these are 2n elements, and since identity square is equals to e, so identity cannot be satisfying this property. Hence, so you will get 2n elements. But the catch again is to prove that x and x inverse are not equal. Okay, the same thing, exactly same thing. And for cubic and for square, the same method of writing, only like whatever you're writing remains, I mean changes. Okay. Now this is another question. I think this will be the last question for this particular video. So this question is about matrices. Why is this important? Because in matrices generally, for with respect to addition, we get as identity element as 0 0 0 0 if it's a 2 by 2 matrix. Okay, and for multiplication we get our identity element as that 1 0 0 1, like diagonal entries to be 1 and rest elements to be 0. But this is a peculiar case when it's a group, but the identity element is not what you're thinking. It is actually 1 by 2 1 by 2 1 by 2 1 by 2. Okay, that's why I've given it as a question. It has come in previous year question of UPSC once. So let's just see this question. Okay, so the question is about you're given a group G which can be written as AAAA, and A are coming from real numbers and A cannot be equal to 0. Otherwise, with respect to multiplication, this would have never been a group, because it would not have been possible to take the inverse of this particular matrices. Okay, because 1 by 0 would not have been defined. So hence the question says that entries are coming from real number and all these entries are same. It's a 2 by 2 matrix and A is not equals to 0. So see, only one line written in mathematics give you at least 6 lines of literature information. Okay, 2 by 2 matrix, entries are same, coming from real numbers, not equal to 0. Okay, so you're getting like almost 5-6 lines of literature equation from one line of mathematics, and that is why mathematics is so powerful, because you can actually write the crux or sum of huge like one pager in just like I think 3 lines. So that is the beauty of maths. Okay. So now you have to show that the group is, the set is basically a group under matrix multiplication. Okay, so basically you have to show that G dot is a set and it is a group. So how do you prove it? 5 properties: non-emptiness, closure, associativity, identity, and inverse. Okay, so that's how you remember. Keep revising it with me so that by the end when I complete the video, you're done with your modern algebra. Okay, this is how it will go. So you will benefit, I'll benefit, and we can both learn with each other. Okay, so now first of all, proving it non-empty. Obviously it's non-empty because there can be infinite number of real numbers that I can put here. Okay, and now operation is multiplication. I always write in this fashion. It just helps me to make sure that I'm doing no mistake. Okay, because sometimes what happens, you copy it from the question paper and then you write addition as your operation, and then you solve the whole question and then you realize that operation was multiplication. There is no space or time to be done that mistake. Okay, so now first of all, closure. So how will you see closure? So you will take 2 elements from that set. So 2 elements here will be looking like matrices. So one will be like AAAA, another will be like BBBB. Okay, 2 by 2 matrices where A and B are coming from real numbers and they are not equals to 0. So all you need to show is that if I multiply A dot B, then even the result matrices will also be lying in the set. So how will you show? You'll multiply it. So you'll get something like 2AB, 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 2AB. And I know that 2AB is also, if A is real number, B is real number, then even their multiplication is also a real number. So their multiplication into 2 will also be a real number. And if A and B are non-zero, then obviously their multiplication will never be 0. So hence, this will satisfy the closure property. Okay, associativity, since it's a different kind of operation and different kind of set, you need to prove it. So you need to take now 3 elements, capital A, capital B, capital C, and prove that A dot B in the bracket dot C will be coming out equals to A dot B and C in the bracket. Okay, so here you can see that I've written it will become something like this, and finally you get the same answer. So associativity is also satisfied. Now next thing is to prove identity. So identity means what? That if you will have to assume some identity element called E, capital E, which will look like E1, E, small e. Okay, and you have to prove that A dot E will be equals to A, and you have to find that identity element. Okay, so here see, can you look at my cursor? So A dot E is equals to E dot A is equals to A. Right? So here if you multiply this A matrices with the E matrices, and if you put it equal to A, so first multiply this and then equate each element. So basically when you are saying that 2 matrices are equal, you're equating their corresponding entries. Okay, so hence you're equating 2AE with A, 2AE with A, and hence you get your identity element matrices as 1 by half, and half is not equals to 0 and half is a real number. Hence identity is also satisfied. And now inverse, same thing, AA inverse is equals to E. And then finally you find A inverse is 1 by 4A, since A is non-zero, hence A inverse exists, and 1 by 4A will also be a real number. Okay, so hence you say that this is a group because all 4 properties are satisfied. The question for you is to see if it is commutative or not. Okay, please reply in the comment box and tell me if it is commutative or not, and we'll continue from the next class from the questions ahead. Okay, thank you and meet you in the next video. Please rate, review, recommend, share, and subscribe to my channel, and see you soon. Thank you.